In the previous video, we took a look at these 6 rules and determined they had a lot in common and that there wasn't a whole lot in the way of memorization that we needed to do. One thing that we might need to know, though, is why there's some of these that have coefficients in front of them. Some of these are weighted, in other words, and some of them are not. For example, f of a is not weighted, and f of b is not, but f of a plus b divided by 2 is weighted. Why is it that some of these are weighted and some of them are not? Aren't all points created equal? Well, let's take a look at that question and see if that is indeed the case. More specifically, let's look at these first 4 rules and see if we can determine something that might help us in understanding why would we want to weight some of these points more than others. So let's start out with let's look at a constant function. Let's say we have this function here. We have our points A and B. We want to know the area of the red portion, and we want to use these rules to get a good approximation for that area, for that integral, for that definite integral. So if we use the left rule, we know this point, this is f of a, and we draw this line across, and we see that indeed that is the exact same thing as the line we had. So we get an exact answer for the integral. Now if we use the right rule, then we take this point and draw a line across again, and again, when we compute the area, it is the exact same as the red area. So the right rule also gives us an exact answer. The midpoint rule means we're just taking the point at this middle, a plus b divided by 2, going exactly in both directions, and we see again that gives us an exact answer. And quite obviously the trapezoid rule, where we actually know 2 points and then connect them, also gives us an exact answer. So all 4 of them work. In the previous video, we wanted to find similarities, and in this video we were looking for some differences that might give us some insight as to why we would weight some of these more than others. We haven't determined any difference here. So a constant function, that is something of degree 0, such as we have here, is obviously not going to help us any, because we haven't determined any differences. Let's look at something of a different degree. Let's take something perhaps of degree 2. Let's draw something like this, for example. Let's say this is A and this is B, maybe. And again, we want to know the area of the red part. If we take the left rule and we draw our line across, we see quite obviously we're leaving out a large portion. So that's not going to, might give us a good approximation, but it's not going to give us an exact answer in any case. So we'll put a little X there to indicate that. If we take the right rule, we take this point and then we take the area of this shape, which quite obviously is way more than we would have needed, so that's also not going to give us an exact answer. So neither one of those works. Let's take the midpoint rule. The midpoint should be somewhere around here probably. And then we have this and this. Obviously we're leaving a whole lot out here, and we're getting a little bit back here, but it's not going to be exact. And the trapezoid rule, obviously if we take this point and we take this point, because the trapezoid rule gives us 2 points, we connect those. Obviously we have a whole lot here that's not part of the actual integral, so we're not going to get any sort of exact answer there either. So we determined that when we looked at polynomials of degree 0, or a curve of degree 0 here, that all of them worked, and then we looked and saw that if we looked at something of degree 2, this parabola here, that none of them worked. So why don't we take a look in the middle? Maybe it will be worth it to take a look in the middle. So that means degree 1, right? So let's take a look and see if we can determine some sort of differences by looking at a graph of degree 1. So I have my axes here and my axes here. That one didn't work. So we'll take a line like that maybe, and we have our points A and B, and again we want to know the area of the red portion, and we'll start again with the left rule. If we take this point on the left and draw our rectangle, again, obviously that's not going to work. Right? We're not counting this portion, so the left rule is not going to give us an exact answer at the very least. Now, let's look at the right rule. We pull this across here. There we're adding way too much, right? So the right rule is not going to work. It was obviously not the right rule, so to speak. And actually, if we just skip to the trapezoid rule, quite obviously, if you have 2 points here and you connect them with a line, then you're going to get an exact answer, right? So the trapezoid rule is going to work. So there we've determined something interesting. Now let's take a look at the midpoint rule. The midpoint must be around here. Now if we take a look at that, I want to do this exactly if I could. There we go. That might be good. At first glance, looks like it's not going to work, does it? I mean, I'm not counting this part here, and I am counting this part. So it doesn't look exact. But if you think about it, these 2 triangles, namely this triangle here and this triangle here, have the same area, because this is a curve of degree 1, which means it has a constant slope, right? So the rise over the run here and the rise over the run here is going to be the same. So if 2 of those 3 sides in the triangle are the same, then the third one's going to be the same, because these angles are also the same. So these triangles have the exact same area. So they're basically just canceling each other out, right? So the midpoint rule does work. Now we were hoping that, or I was hoping that just one of them would work, because then at least we would have known something about that this rule is somehow better than the other ones. But we have 2 of them that worked. So it might seem like we're not through, but actually we are, because the trapezoid rule needed 2 points in order to get that correct answer, and the midpoint rule only needed 1. The midpoint. What's so special about the midpoint? Well, you might think of it like this. If you know the middle point of any sort of crazy function, let's say here's A and this is B. If you know the middle point, then you know a little bit something about how the point got there, and you know a little something about where it's going. Whereas if you just know the first point, you just have some information about where it's starting. And the same goes for the last point. Now, that's not a very exact mathematical representation of why the midpoint is so important, but that might be an intuitive way of grasping that this middle point is indeed different than the left point or the right point, because all three of these, the left rule, the right rule, and the midpoint rule, all three of those just use one point. So it's interesting that the midpoint rule actually will always give us an exact answer for any curve of degree 1. So that's interesting about the midpoint. So now, what does that have to do with our goal of before, which was to see why some of these got more weight than the others? Well, which ones are getting more weight? F of A is not getting any extra weight. F of B is not getting extra weight. Which one's getting the extra weight? The one in the middle. The same thing if we look at Simpson's second rule. F of A, F of B, no extra weight. Which ones get more weight? The ones in the middle. And these two here are not exactly in the middle, they're only at the thirds, but they're also getting slightly less weight in comparison to the middle, right? This point here, a plus b divided by 2, was exactly in the middle, and it has 4 times as much weight as f of a, for example. This one is only at the point a third over toward b, and it has 3 times as much weight as f of a. The same thing goes for that here. So, at least intuitively speaking, it would seem to make sense. The closer these points are to the middle, the more they would be weighted. So, it might be worth it to take a closer look at the middle.